Factors affecting solubility. First, let's look at how pressure affects the solubility. As the pressure increases, gas solubility also increases. The relationship is called Henry's law, and our equation is P equals K times C, where P is the partial pressure of the gaseous solute above the solution, C is the concentration of the dissolved gas within the solution, and K is a constant for the specific solution. And notice when we look at this particular equation, the partial pressure of the gaseous solute and the concentration of the gas in the solution are directly proportional. Now, Henry's law works best when we're looking at diluted solutions. The solute doesn't dissociate in the solvent, and the solute doesn't react with the solvent. So let's look at an example. It says a certain soft drink is bottled so that a bottle at 25 degrees Celsius contains carbon dioxide gas at a pressure of 5.0 atmospheres over the liquid. Assume that the partial pressure of carbon dioxide in the atmosphere is 4 times 10 to the minus 4 atmospheres. Calculate the equilibrium concentration of carbon dioxide in the soda both before and after the bottle is opened. And it tells us that our constant is 32 liter atmosphere per mole. All right, so we're going to take P equals KC, and for our closed soda bottle, we've got 5.0 ATM equals 32 liter ATM per mole times C. So we're going to divide both sides by 32 liter atmospheres per mole, and we're going to get 0.156. Now notice that the atmospheres are going to cancel out. We're going to be left with moles per liter, which is molarity, and that's our concentration. Okay, now we open our soda up. We establish equilibrium with the atmosphere, and we want to find out what the new concentration is. So we have our same equation, P equals K times C. Now our pressure is 4.0 times 10 to the minus 4 atmospheres. Our K is a constant, so it's the same, 32 liter atmosphere per mole. And we want to calculate what our new concentration is. So we divide both sides by 32, and we get our new concentration is 1.25 times 10 to the minus 5 moles per liter, or molarity. So notice that when we open our soda up and we establish equilibrium between the pressure in the gas and above the gas, our concentration goes down, and that makes sense because soda goes flat after we open it up. Now let's look at the effect that temperature has on solutions. As the temperature of a liquid increases, the ability of the solute to dissolve increases. Well, sometimes it does, and sometimes it doesn't. So if we look at this graph here, we've got temperature along the x-axis, and we've got solubility along the y-axis. And solubility is in terms of grams of solute dissolved in 100 grams of water. And if we notice, for most of the solutes in water, as the temperature goes up, the solubility goes up. And that's typical, especially when the solute is a solid. But we do have a couple of solutes that are a little bit different. Sodium sulfate and cerium sulfate, as the temperature goes up, the solubility goes down. And that has to do with the interaction between the solute and the solvent particles. Now, another thing we should be familiar with, and it's not on this graph, but when we talk about gases as our solute, As temperature goes up, solubility typically goes down. Now we want to talk about Raoult's law. And what Raoult's law has to deal with is the partial pressure of a particular solvent relative to the partial pressure of a solution. So our P solution is the observed vapor pressure of the solution. We've got our mole fraction of our solvent. Now notice there, it's not the solute this time. We're talking about the solvent, which is typically water. And we've got the vapor pressure of the pure solvent. So let's look at an experiment. Over on the left-hand side, we have a closed container with a pure solvent in it. Doesn't matter what the solvent is. We could say it's water. Doesn't matter. We know that the solvent will begin to evaporate and the pressure above that liquid will increase. As the gas particles above the liquid increase, condensation rate increases, and we get to equilibrium when the rate of evaporation equals the rate of condensation. So we've got this system on the left-hand side at equilibrium, and it tells us that the pressure is 3. Whatever it is, atmospheres, doesn't really matter. Then we add a solute to the solvent. So over on the left-hand side, right-hand side, we've got non-volatile solute particles dissolved in our solvent to make a solution. And those non-volatile solute particles are going to form intermolecular forces with the solvent particles and prevent some of the solvent particles from evaporating. That means that when we establish equilibrium, our vapor pressure is going to be less in the solution than it was in the pure solvent. So let's look at another experiment. Let's say that we have 2 beakers. We place them into a sealed container. One of the beakers contains pure water and the other contains salt water. Okay, so over on the left-hand side we start out. We've got our beaker on the left with pure water in it, and we've got a beaker with a solution on the right-hand side. Now the vapor pressure of the water is greater than the vapor pressure of the solution. So the water is going to try to achieve equilibrium by evaporating. The salt water is going to try and reach equilibrium by condensing water into our solution. And what will happen eventually is we'll have no water on the left-hand beaker, and all the water will have condensed in the right-hand beaker. So this proves that the presence of a non-volatile solute lowers the vapor pressure of a solvent. The solute lowers the number of gas particles that can reach the surface and turn into vapor. So the vapor pressure of the water is greater than the vapor pressure of the salt water. Now let's look at a problem again. Let's say that we've got C3H8O3. It doesn't matter what that is, but it tells us it's a non-volatile liquid. What is the vapor pressure of the solvent solution made by adding 164 grams of this glycerin to 338 milliliters of water at 39.8 degrees Celsius? And it tells us that the vapor pressure of pure water at 39.8 degrees Celsius is 54.74 torr, and the density of pure water at that temperature is 0.992 grams per milliliter. All right, so we're dealing with a vapor pressure for a solution. So let's start by writing down our equation. P for our solution equals the mole fraction for our solvent, which in this case is water, times the vapor pressure of our pure water. So we're told how much solute we have in grams. We have 164 grams of our solute. 1 mole of that solute is 92.11 grams off the periodic table. So that's going to give us 1.78 moles of our solute. It tells us we have 338 milliliters of our water. We need to get that to moles. Well, it tells us the density, 0.922 grams of water for every 1 milliliter of water at this particular temperature. And then 1 mole of water is 18.02 grams of water off the periodic table. So we have 18.6 moles of water. Now we can figure out our mole fraction for our water. We're going to take 18.6 and divide it by 18.6 plus 1.78. And that's going to give us 0.913 for our mole fraction. So now the vapor pressure of our solution is going to equal 0.913 times the vapor pressure for pure water at that temperature, 54.74. And we're going to get 49.97 torr for our vapor pressure for our solution. And that makes sense because when we add the solute to the solvent, it's going to lower our vapor pressure, and it does. So what if we have a solute that breaks up into ions? When a substance breaks up into more than one ion, it essentially has a multiple effect than it's supposed to have. So for each particle it breaks up into, we're going to have more of a change in our vapor pressure. So let's look at this as an example. What is the vapor pressure of a solution made by adding 52.9 grams of copper 2 chloride to 800 milliliters of water at 52 degrees Celsius? And it says that the vapor pressure of water at 52 degrees Celsius is 102.1 torr, and its density is 0.987 grams per milliliter. All right, so we're trying to find the vapor pressure of our solution. So we'll start with our equation. The vapor pressure of our solution equals the mole fraction of our solvent, which is water, times the vapor pressure for pure water. So we have 52.9 grams of copper chloride that we're dissolving in our water. But copper chloride is an electrolyte that's going to break up into ions. So our first step, 1 mole of copper chloride is 134.45 grams of copper chloride. And then for every 1 mole of copper chloride, we're going to have 3 moles of ions. That means our effect is going to be 3 times. So 1.18 moles of ions. Now we're going to convert the 800 milliliters of water to moles. So we'll use our density first, 0.987 grams for every 1 milliliter at that particular temperature. And then 1 mole is 18.02 grams. So that's going to give us 43.82 moles of water. Now we can figure out our mole fraction for water. We'll take 43.82 and divide it by 43.82 plus 1.18. And that's going to give us a 0.975